Okay, we're going to look at an example here for marginal analysis. And we are given this function for x. It's the number of saws sold at a price per dollar, or price in dollars p per saw. And then a function c of x, which represents the total cost in dollars of producing x saws. Switch colors here. Okay. Part A. So we have I different parts of this problem. Part A is to write P as a function of the demand X and what is the domain. So if X is the number of saws sold at a price P and we want P as a function of X, then really all it's saying is solve for P. So we have X equals 6,000 minus 30P. I would, add 30P over here and subtract X. Okay, I just rearrange, right? Simple addition and subtraction, and now divide both sides by 30. Remember to do every term. So we get, 200? Yeah, 200 minus x over 30, or sometimes we prefer to write it as 1/30th x. Either way. All right, now what is the domain? So let's see. I know x has to be greater than 0, right? So let's start there. X, you're not going to set a price at 0, but technically I guess you could. So we know that. And then what else? So I also know the price can't be negative, right? So I know, so domain is in terms of x, but like intuitively I know this has to be true. But also p has to be greater than 0, right? I can't have a negative price, so I'm going to produce more than 0, x greater than 0, but also p has to be greater or equal to 0. So what I'm going to do is just set this price function equal to 0 and solve for x. So we could do 1 over 30 x equals 200, right? Just move this to the other side, multiply by 30. So once I go beyond 6,000, like I knew that was a breaking point, right? Once I go beyond 6,000, the price would be negative, right? The larger x goes here. So therefore, the domain is between 0 and 6,000. Okay, there's the work for A, the marginal cost. So anytime you see this marginal cost, revenue, or profit, you should think derivative. Okay, what that is saying is C prime of X. The change of cost if we were to increase production by 1, right? That's derivative, the instantaneous rate of change. So looking at that, I noticed I just wrote this problem wrong as well. It didn't affect the answer to part A. But I'm taking an example out of the book, and there's a 60 there. Okay. So the marginal cost, the derivative of this guy is pretty easy, right? The derivative of constant is 0, and the derivative of 60x is just 60. So I don't even think we need to do work there. Marginal cost is 60. Find the revenue function and state its domain. All right, so revenue is if we took the cost, P, and multiplied it by however many we sold, right? So there is a function R of X equals X times B. How many units and then the price for each. So, if you're selling candy bars at $1 each and you sell 10 of them, then you just do 10 times 1, 10. So now that we have this in terms of functions of X and P, all we need to do is take that P function that we had here and multiply it by X. So R of X equals 200X minus 1/30 X squared. Okay, again, we just took P and multiplied by X. And what is that domain? Well, I know it has to stick within the original 0 to 6,000 because that was the original domain. So revenue can't be negative, so we could set this equal to 0 and see what happens. Let's go and give that a try. Oops. So if revenue is 0, again, we want that greater or equal to 0. 200x minus 1/30 x squared. So I'm going to add this to this side. And just to make that positive, honestly, let's see here. We don't really need to do that. If I'm solving that for x, it don't matter, but let's eliminate a step, why not? So 200, right, factor out of x minus 1/30x. So why would I do that? Because now x equals 0, right, is one solution, or all that equals 0. And now you could see where I was going originally, and I just backed up. To make it, technically we should be factoring, so that's why. So multiplied by 30, again we get 6,000. So that domain doesn't change. That kind of makes sense. All right, R prime of 1,500. Next is the marginal revenue, my bad. So marginal revenue is just the derivative of the revenue function. So we need R prime of X. And looking right above R of X, if we took the derivative of this guy, right, derivative of 200x is easy, that's 200. The next part though, we bring down the 2 and we drop 1, so negative 2 over 30 is just negative 1/15, right, simplified 2 over 30, and then x because we dropped an x. Okay, so there's the marginal revenue. R prime of 1,500, that simply means substitute 1,500 in for x. So R prime 1,500 equals 200 minus 1/15 multiplied by 1,500. So that's going to be 200 minus 100, which is 100. So what does this mean? So at a production level, X is 1,500. So at this production level of 1,500 saws being produced, the revenue increases about 100 per saw. Okay, so let's write that out. At production level of 1,500 saws, we see an increase of approximately $100 per saw. All right. So 4,500 would be the same thing, but we're substituting 4,500 in for x, that same function. R prime of 4,500 is 200 minus 1/15 times 4,500. So we'd get 200 minus 300 for a result of negative 100. So just substituting these new values at a production level of 4,500 saws, we actually see a decrease of approximately $100 per saw. So we don't want to produce that many, right? We start losing revenue. I mean, in the long run, it's all about profit, but I assume if we're losing revenue, we might be losing profit. Part F, graph the cost and revenue function on that domain 0 to 6,000. Find these break-even points and the regions of loss and profit. Okay, I opened up GeoGebra. This is a convenient free graphing calculator app. Feel free to use it if you don't have a graphing calculator. And all I did is I put in, to save a second, I put in the two functions in for F and G. Okay, so F is the cost function, G is the revenue. So anytime the revenue is above the cost, then we have profit. Anytime it's below, we have loss. So I'm going to do a very rough sketch back on the other page to explain that a bit further. Okay, so again, rough sketch. I don't remember where exactly this was at, something like this. All right, this region here, the cost, right, the cost is in green, is greater than the revenue. So I'm at a loss there. The same thing here on this region. The cost is greater than the revenue, which means we lose money. But in this region here, the revenue is greater than the cost, so that means we have a profit. Right, so that is those regions we are looking at back there in GeoGebra. To find these break-even points, we need to find where those two functions are equal. Okay, they're there and there. So that's where is cost equal to revenue, and that happens twice here. Well, I'm going to be a little lazy and not actually solve this mathematically because we have technology. Let's use it. This is pretty cool. You can use this tool feature here and intersect, and then you select the two functions, and it gives me 2 points, A and B. And it tells you those 2 points. A is 600, and then 108,000. And B darn, it's cut off a bit. There we go. 3,600, 288,000. Okay, those are the break-even points. We won't lose money, we won't profit any money because both functions are equal. Okay. So on the graph, right, I can't draw in GeoGebra for this video, but I explained where those regions of profit and loss are. The break-even points, as we said, there were 2. Again, that's where the cost equals the revenue, and that happened at 2 points. We had the first one was X was 600, the Y was 108,000. The second break even, I'm just going to put BE, break even point, was at 3,600 and 288,000. Okay. And that's why in that previous one, that our prime of 4,500, our marginal, we were actually losing because we were out here in this region. right? We were beyond 3,600 for X. We're at 4,500. Anywhere between 3,600 and 600 and 3,600, we're profiting. Okay. Moving on. G, we want the profit function. Profit, remember, is revenue take away the cost. And it could be negative if cost is greater. So we have both of those functions. So the revenue is 200x minus 1/30th x squared. Subtract, that's the revenue function. Subtract the cost function, 72,000 minus 1/30th x. Okay, that's from above. That was in the problem. Oh no, 72,000. Sorry, the cost was plus 60x. I was reading that wrong. 72,000 plus 60x. So therefore we get, let's go in descending order, negative 130x squared, 200x minus 60x is 140x, and then subtract 72,000. Okay, that's our profit function. Marginal profit, derivative. Okay, so the derivative, again, bring down that 2, we get negative 1/15th x plus 140, and then the derivative of that is 0. Derivative of a constant is 0. The last part is to substitute 1,500 and 4,500 into the marginal profit function we just did. So P prime 1,500. All right. So that is negative 100. When we combine these two, we get negative 100 plus 140. So we get 40. All right. So what does that mean? That means at a production level of 1,500 saws, okay, production level of 1,500 saws, okay, we see an increase of $40 per saw, increase of profit, since that's marginal profit. Okay, so remember the revenue at that point was we were bringing in 100, but we still had costs. So after all the costs, we profited $40 extra. Now when we go to 4,500, we should see a loss. Negative 1/15 times 4,500 plus 140. So that's negative 300 plus 140. So negative, I'm going to put units there because I'm not going to rewrite it. So we get a loss, right? We're losing about $160 per saw if we are producing 4,500. That's pretty significant.